like temporomandibular disorders, that's the first one. Is there something wrong with someone's temporal bone, their temporalis muscle, their mandible? What specifically does that mean? Better stated, we're going to look at trigeminally mediated disorders. Everything that we look at in this particular field is mediated by the trigeminal nerve. We just haven't been paying very close attention of the capacity that this nerve has and the impact and influence it has on our patients. Our typical daily relationship with the trigeminal nerve in general dentistry is to try to conceal from the sensory nucleus what we're doing out there. You're not going to sink a burr into someone's pulp canal unless you've totally blocked sensory information to the sensory nucleus. So you get those things completely anesthetized. Can you imagine if you could strap somebody down, drop a burr into their pulp canal, have them scream like crazy, but they can't move because you got them strapped down? Man, that hurts. When you take that burr out, it still hurts. Later on that day, it'll ache like crazy. You have had an assault on the trigeminal sensory nucleus. But if you had anesthetized them ahead of time, the sensory nucleus doesn't even know what's going on out there. So without profound anesthesia, if someone's hurting during your procedure, they tend to be achy and headachy later that day. This lecture isn't going to talk about migraine prevention, but what I just touched on is a noxious assault on the trigeminal sensory nucleus. Neurology has been searching for a way to relieve the sensory nucleus from getting noxious input on a regular basis. They think if they could figure that out, they could reduce migraine frequency. And NTI does that by suppressing what clenching provides to crushing the PDLs, muscle hyperactivity, et cetera, joint strain, which relieves noxious input to the sensory nucleus. There's my NTI migraine lecture for today. So now we're trying to, in dentistry's relationship with the trigeminal sensory nerve is to block any information to the nucleus. So once you've blocked all this, take a look at this Gray's diagram when it talks about the motor route. That's all you're really going to see. No one really talks about motor intervention to the muscles of elevation. A little review on our muscle physiology. Muscle force, how much force does this muscle generate when it begins to contract? It's controlled by the neuron action potential recruitment, meaning how many fibers are innervated within that muscle. The recruitment follows the size principle. The more fibers that are innervated, the more force that will be created. So the more fibers that are innervated, the larger the motor unit becomes and the more force that is generated. They used to rate light in candles or lumens, foot candles. One candle, it's either the candle's lit or it's not. If all of the candles lit, you get a lot of light. The percentage of fibers that are contracting dictates how much force is being generated. Here's observing the gastrocnemius of a cat and how the muscle system works. And we're going to look at, this is going to be a muscle here, and it's going to represent the fibers that illuminate here that are being innervated. So to stand quietly, 25% of the motor neurons in a cat's leg are innervated. It's just standing there quietly. It doesn't need any more than that. To run, 20% of the force is generated with half the fibers being innervated. To jump, almost all the fibers are innervated. That's as much force they can be. Boing, up they go. When we're walking, I'm 200 pounds. My legs, as I walk forward, aren't trying to propel me faster than a walking speed. If I wanted to run, I have to use more muscle force. You probably thought there was going to be a step in front of you, and if I thought there was a step in front of me, I have to get more than 200 pounds of force to elevate myself any higher than the floor. When you think there's a step there and you go, boom, oh, sorry, I thought there was a step there. Your leg was anticipating more than 200 pounds of force necessary to elevate you. So your muscle worked much harder than it needed to. The purposeful necessity will dictate the degree of muscle innervation. What you need to have done is how much muscle fibers that will be innervated. So here's the motor root, and we're going to innervate the temporalis muscle. And here's an EMG device monitoring the amount of electricity that's underneath these electrodes. And I like to call the teeth these circuit completion devices, where you can complete the circuit that we're going to, in order to allow innervation of the temporalis muscle. When the incisors are contacting, only enough innervation is allowed for about 30% of maximum force. You can't get more than that. If you only have incisal contact, you can only get about 30% of force generated. If the canines are contacting, you can get about 75% of the force because more fibers are being innervated. The maximum force that can be generated is when the molars are in contact. When we talk about the rules of parafunctional control, and there's only 2 of them, the first one is to minimize the intensity of muscle contraction. The way you minimize muscle contraction intensity is you eliminate the ability to innervate the fibers. The minimum amount of fiber intervention happens when there's incisor contact. So now let's take a look at a little different perspective here. If you've got someone with their mandible at rest, and you ask them to raise their mandible a little bit, and you've got them on an EMG, you're going to watch as the electricity underneath these electrodes is increasing as they elevate their mandible. And Barry has a great video of that with a patient. He's got them wired up. He goes, close your mouth a little bit more, and you'll see as they start to elevate their mandible, although there are more fibers contracting, you won't see anything on the EMG. It's not even enough to show on a device that's looking for a reading. It's not even there yet. You can get someone to actually get their teeth to touch and not get much increase. So you have to ask them, all right, look, I want you to start clenching as hard as you can. We'll call that maximum clenching voltage. That's even in the literature, MCV. So this electrode is now seeing underneath it the percentage of fibers underneath it that are actually being innervated. And and in this particular example, there's a degree of microvoltage that we'll see on this. If you put a full covered splint, everything's touching all at the same time, and you say, ready, clench as hard as you can, they'll be able to generate more voltage. It's even a more forceful contraction. You know why I think that is? I think there's purpose in having something between your teeth. When your teeth are together, what are you doing? What's the design in that? Why is that purposeful? Why should that be the most powerful, forceful thing you can do if your teeth are together? What does it do for you? You need to have something in between your teeth. That's what they're designed to do. So true maximum clenching voltage is with the teeth slightly apart. Something's in there allowing them to communicate. If you remove the anterior segment, it's just all molars, you still get maximum clenching voltage, the most fibers that you can innervate. Now, as I move this back and forth, the condyle, the mandible, there's no positional change at all. The only thing that's going to change here is the circuitry completion. We're going to unplug these molars. They're not going to touch each other. We're going to plug in the incisors instead. Nothing else moves. And you still ask the patient, still squeeze as hard as you, this is as hard as you can, right? Nothing else will change, but you'll have a drop in intensity.